In this lecture, we will define a natural map from the visualization from a group to H1X and show that it is an isomorphism. So recall that if G is a group, then G abelianization is defined to be G of the commutative subgroup, where is the normal subgroup. Generated by elements of the type G1, G2, G1 inverse, G2 inverse. So let us recall the following result. Which we proved earlier. Suppose f and g are two maps from x to y such that they are homotopic. Then the induced maps on chain complexes f dot comma g dot from c dot x to c dot y are homotopic. In particular, there are maps Tn from Cnx to Cn plus 1y such that Fn minus Gn is equal to Pn minus 1 composed Tn plus Tn plus 1 composed Tn. So let us define a map phi from pi 1x x0 to h1x. So let f be a loop at x0. Then we may view f as defining a map from say I to x such that f of 0 is equal to f of 1 is equal to x0. Thus d1 of f is equal to 0 and defines a homology class f bar in h1x. So we define phi of f to be equal to f bar. So we need to check that if f is equal to g in pi 1 xx naught, then phi of f is equal to 5g. Let f and g be two maps from S1 to X, which are homotopic. So that is, there is a map f from S1 cross I to X such that f restricted to S1 cross 0 is f, and f restricted to S1 cross 1 is g. Then we have f1 minus g1 is equal to b0 compose d1 plus d2 compose b1, and both these are maps from one change in S1 to one change in X. Let gamma from I to S1 denote the map gamma of t is equal to the power 2 pi I t. Then gamma is an element of Zeeman chain and it's closed. So applying the above equation, the above to gamma, we get f1 of gamma minus g1 of gamma is equal to d2 compose b1 of gamma, and this is in c1x. But note that f1 of gamma is by definition f compose gamma. And clearly p of f compose gamma is 0, and the class f bar is by definition the class defined by f compose gamma or f1 of gamma. So this shows that f bar minus g bar is equal to 0 in h1x. Thus, f bar is equal to g bar. Thus, phi of f is equal to phi of g. So This defines phi from pi 1 x x naught to h1 x. Next, let us check that phi is a group homomorphism. So we need to show that phi of f star g is equal to phi of f plus phi of g. So consider the maps. So the first map is the linear map, which sends v0 to 0, v2 to 1, and v1 to half. So denote the composite. And the second map is just f star g. From 0 to half it is f, and from half to 1 it is g. So denote the composite. Sigma from delta 2 to x. So then T2 of sigma is sigma restricted to v1 v2 minus sigma restricted to v0 v2 plus sigma restricted to v0 v2. This is equal to f minus f star g plus g. So since all f, g and f star g define homology classes, it follows that in h1x we have f star g power is equal to f power plus g. That is, phi is a group homomorphism. So thus phi factors uniquely as, since h1 x is abelian, so next we will show that phi bar, that phi is surjective. And this will imply that phi bar is surjective. So homology class homology class is represented by an element beta, which is of the form AI sigma I, where AI are not zero integers and sigma I are continuous maps from delta 1 to x. So there is a homology class in each one. For sigma from delta 1 to x, denote by sigma tilde the map given by sigma tilde of t is sigma of 1 minus t. Then it can be checked easily that sigma plus sigma tilde, a priori there is an element in C1x, defines is in the boundary image of T2. Thus, if some of the AI is strictly less than 0, then we may replace sigma I by sigma I tilde and assume that beta is equal to I equal to 1 to n AI sigma I, where all AI are positive. So since T of summation I equal to 1 to n AI sigma I is 0, we can arrange the sigmas as sigma 1, sigma 2, to some sigma m. So some of these may repeat. These may repeat, may be equal. And such that sigma I of 1 is equal to sigma I plus 1 of 0 for I strictly less than n, and sigma 1 of 0 is equal to sigma n of 1. So the picture looks like this. There is sigma 1, sigma 2, sigma 3, and so on. And this is finally sigma. So let alpha be a path from x naught to sigma 1 of 0. We will show that phi of alpha star sigma 1 star sigma 2 star alpha tilde is equal to class of this sigma m. So let us denote this loop by gamma. Note that both alpha star, gamma star, alpha tilde and gamma are homotopic. But the homotopy does not keep the point x not fixed. In fact, these are loops based at different points. So from what we saw earlier, it follows that the classes alpha star, gamma star, alpha tilde, bar and gamma bar are equal in h1x. Since phi of alpha star, gamma star, alpha tilde is equal to alpha star, gamma star, alpha tilde bar, it suffices to show that gamma bar is equal to bar. For this, it suffices to show that gamma minus sigma I is an image of T2. But note that the same idea we used to show phi is a group homomorphism shows that if f and g are two parts such that f of 1 is equal to g of 0, then f star g minus f minus g is an image of T2. So applying this repeatedly, we get belongs to image of T2. So this proves that phi of alpha star in h1x. Thus, phi is surjective. Finally, we show that phi is injective. For this, we define a map psi from C1x to pi1x x0 relinealization. So it follows. It suffices to define this map on the generators. So we fix once and for all. Paths alpha x from x0 to x for all x and x, and such that alpha x0 is the constant path at x. So define psi of sigma equal to alpha sigma 0 star sigma star alpha sigma 0 tilde. So let us first check that psi is 0 on the image of T2. So for this, theta PMF from delta rho to x, then T2 of theta is equal to theta restricted to so let's say the image looks like this. So this is theta of V0, theta of V1, theta of V2. So thus psi of T2 of theta is equal to alpha theta of V1 star sorry, there's a typo here. So a sigma of 1 alpha theta of V2 tilde. This start with inverse and this is clear is alpha of theta V1 star theta restricted to V1 V2 P0 V2 inverse theta restricted to P0 V1 alpha of theta of V1 tilde. But since theta, this loop is homotopic to the constant loop at theta of v1. It follows that psi of t2 of theta is 0. Thus, psi defines a map from C1x mod image of T2 to R1 XX1 booleanization, and each one x is contained inside this group, and we can just restrict psi to this. So this defines psi. So now we will check that psi compose phi bar is equal to identity of R1 XX1 booleanization. So let's take a class f in the booleanization. So it's going to be represented by some loop f. Then phi bar of f is equal to f bar, which is in h1x, and psi of f bar by definition is, we have to take the starting point of f star f star alpha x naught tilde. But since alpha x naught is just the constant loop, this is just equal to c x naught star f is equal to f. So this shows that psi compose phi bar is equal to identity. So this means phi bar is injective. So thus, since we already seen phi bar is surjective, is an isomorphism. And let us make some final remark that h from x to y be a continuous map. Then there is a commutative diagram. So this follows easily. So this H low star. This follows easily from the definitions. Since phi y compose H low star of a loop f is equal to phi y of H compose f. This is H compose f bar which is exactly equal to h to the star of f bar. Of f. So we will end here.